Assalamu alaikum guys, hope all of you are fine and you're staying indoors, staying safe. Today we will be discussing chapter number 3, that is infinite duration impulse response filters. We'll be rather starting this chapter. So today in this lecture, in the first lecture for this chapter, I will be discussing the basics. Right? So if we think about filters, if we talk about filters, basically there are two types. Filters are of two types. One is FIR filters, other one is IIR filters. Now the filters which make use of feedback, they are called recursive filters. Right? And then we will be having another class of filters which don't make use of any feedback. Right? The recursive filters, they have impulse response that is of infinite duration. Impulse response is of infinite duration. Right? Okay. So we have recursive filters in which feedback is used, and the impulse response is of infinite duration. They are also called as IIR filters, infinite impulse response filters. So this is for these three things are for IIR filters. Fine. So now we have another set of filters. They don't employ. So filters which don't employ feedback. Right? These are called non-recursive filters. They are also called as FIR filters, that is finite impulse response filters. As the name suggests, so impulse response is of finite duration. Fine. So in case of now coming back to the IIR filters, in case of IIR filters, the impulse response is obtained by taking inverse Fourier transform of ideal frequency response. Fine, so let me come to the next page. So there are basically several techniques for design of IIR filters. Right. one of the most popular methods is method is first designing a digital filter in analog domain, and then converting to digital domain. Now, this is done because analog design techniques, they are well developed in comparison to the digital design techniques. So when we discuss about designing IIR filters, first we will design the IIR filters in analog domain and then convert the filter from analog domain to digital domain to obtain the digital filter, because basically what FIR and IIR filters are, they're design methods for designing digital filters, right? So next, okay, now we'll be discussing the requirements for transformation. That is transformation from analog filter to digital filter. The digital filter which we had designed in analog domain, and then how are these? What are the various characteristic equations that describe the filter in analog domain? Now the first, so we write system function describing an analog filter. It can be written as, maybe written as HAS. This is the transfer function. This will be equivalent to output divided by input. This is equivalent to summation k running from 0 to m k sk divided by summation k running from 0 to say n samples AK and BK, they are basically their filter coefficients or filter coefficients. Again, another equation, impulse response, that's h of n. Impulse response of these coefficients, that is AK and PK, are related to HAS as, so I'll write it down as HAS is equivalent to integral minus infinity to plus infinity h of t e raised by minus st dt. That is integral of Laplace transform of impulse response. So now let me go to the next page. And the third equation is, if analog filters have a rational system function, that is, say, HAS rational system with an HAS, which was this HAS. This HAS, it can also be described by summation k running from 0 to n ak d by dt or kth order derivative of yt is equal to summation k running from 0 to n pk d by dt of kth order. So this xnt and y of t are input and output of a filter. So basically we got three equations. One is this one, second is this one, and third is this one, right? So there are three equations which describe the filters in analog domain. So on the basis of these three equations, three different types of design techniques can be developed, right? So these three equations lead to three types of design techniques, right? Okay. Oh, there's only one restriction as far as the design is concerned. That's why when we design the filter in analog domain and then convert into the digital domain, the only restriction is that the filter should be stable and it should be realizable. So I can say these three equations lead to three types of design techniques with the restriction that filter should be stable and realizable. Filter should be stable and realizable, right? Okay. Now let us discuss the conditions for stability and causality in analog domain. So for stability and causality, this is something we should know. Analog transfer function should satisfy, say I write them down, following conditions. It's number one. First, number one is HAS, that is the transfer function in analog domain, should be a rational function. Should be a rational function, right? And the coefficients of S should be real, and coefficients coefficients of S should be real. This is number one condition. Number two condition is the poles, you already know this, the poles should lie on left side of S plane. Number 3 is number of zeros. Number of zeros should be less than equal to number of poles. Fine, so these are the three conditions. Now let me go to the next page. Okay. So there are three conditions for stability and causality. One, transfer function should be rational function. So transfer function should be rational and the coefficients of S should be real. Second, the poles should be on the left of the S plane. And the third is number of zeros should be less than or equal to number of poles. Now coming to the digital filter. For digital filter, conditions are digital filter conditions are so since we are designing the digital filter from analog filter, now the analog filter should be stable and causal, right? So the digital filter should also be stable and causal because it's obtained from analog filter. So number one condition is transfer function should be stable. And the transfer function in digital filter will be in Z domain, right? Z transform. So I will write here H of Z should be a rational function, right? And coefficients of Z should be real. Should be fine. Number two is here it was in Laplace domain. It was the poles should be on the left of side of S plane. So that translates to the inside of the unit circle in case of Z transform. So I will write here the poles should be inside the unit circle, fine. So and the third case is the zeros. Again, number of zeros should be less than or equal to number of poles. So I derived these three conditions. These are for the digital filter from the conditions of analog filter. Because why? Because we are transforming from analog domain to digital domain. Basically, we are designing a digital filter in analog domain, and then we are converting that into the digital domain, right? So the conditions should be similar, right? So now these are the three conditions for analog filter. These are the three conditions for analog domain, and these are the three conditions for digital domain, right? So now if you want to map the transfer functions, that is if you want to go from the Laplace domain to Z domain, what should be the conversion rules, right? So the conversion rules, or I will say mapping rules, right? So the first thing is that the imaginary axis in S plane should map into unit circle in Z plane. So this is the first condition. So why is it necessary? So that there is direct frequency relationship. Okay. The second condition is the left half of S-plane. S-plane, if you know, the left half of the S-plane is basically the poles are on the left half of the S-plane, right? So if you see the second condition in digital domain, the poles should be in the unit circle. So I can say the left half of the S-plane should map inside the unit circle, right? So if these two conditions are satisfied, then I will say stable analog filter will be converted to stable digital filter. Now, so what we obtain because of this transformation, since the three conditions will be satisfied, the three conditions of S domain and the three conditions of the Z domain. Therefore, these conditions were basically for a physically realizable, causal and a stable filter. So I can say a physically realizable, stable and causal filter will be obtained. But this filter, the filter which is obtained, so I'll say a stable, causal and physically realizable filter is obtained. But this filter will have one restriction, that is, it can't have linear phase, and we'll see why. So the condition for linearity for filter to have linear phase is that it should be h of n should be equivalent to h of capital N minus 1 minus n, that is, n is the number of samples, or it's the length of the filter. So n is basically equivalent to length of filter, that's the number of samples. Okay. So for this to be satisfied, for every n, for every pole, there will be a mirror image. So every we know every pole should be inside the, for stability, every pole should be inside the unit circle. So for every n, we have a mirror n. So for every pole, we have a mirror pole that's outside the, that will be outside, that's minus, that will be outside the unit circle, and then in that case the filter will be unstable. So so we cannot have a filter having linear phase. Why? Because for every pole inside unit circle, we will have a mirror pole outside, right? So it leads to instability. So this will result in having a unstable filter, right? So a causal and stable IIR filter will never have a linear phase. Fine. So when we design the IIR filter, the only component desirable is the magnitude response is specified, and we are not concerned with the, and whatever phase response we obtain from it is accepted. Why? Because we cannot have linear phase. We know we will always have non-linear phase, right? Why? Because the condition h of n is equivalent to h capital N minus 1 minus n, it cannot be satisfied. If it is satisfied, it means the filter has linear phase. It means that there will be some poles outside the unit circle, which in turn means the filter will be unstable. But we want the filter should be stable, right? So we are concerned with the magnitude response while designing the IIR filter, and whatever the phase response is obtained, we accept it. Fine. So now let me go to the next page. Okay, so let's draw. So this is as far as the designing of conversion rules for designing of IIR filters. Now let's discuss some. As I already said in the beginning, this is the basic lecture of filters. So let's discuss some similarities. Some differences between digital filter and analog filter. So let's come to the number. Let me draw a line. So number one difference is, obviously it's digital in nature, so it operates on digital samples, obviously, right? Digital samples, right? Or I can say, or sampled version of the signal. Right? So analog signal, it operates on analog signals, obviously it operates on analog signals, or I can say these are the actual signals. Why? Because whatever signal you are getting, it will be in analog domain, obviously, and then you do sampling and quantization and then convert it into digital domain and feed that to a digital filter. So digital filter operates on synthesized signals which have been converted, whereas the analog filter operates on the actual signals. So number two is, so it's governed, the equations used here will be governed by linear difference equations. Right. So and this will be governed by differential equations. Right. And number three, it will consists of adders. You've already seen it. Multipliers, right? Delay and delay elements. These things, the adders, multipliers and delay elements, they are either implemented in hardware or software or both. Okay. So it will this thing consists of electrical components only. Analog filter consists of electrical. There is no implementation in hardware, software. It's only hardware. Electrical components like resistors, capacitors, inductors, so on and so forth. Capacitors and inductors. And number four, now in this case, in digital filters, filter coefficients are designed. Coefficients are designed to satisfy desired frequency response. In analog filters, approximation problem is solved to satisfy the desired frequency response. Right. So we have four differences. One is obviously digital filter will operate on digital samples. It will be governed by the linear difference equation such as x of n is equal to y of n minus y of n minus 1, so on and so forth. Whereas it will be the analog filter will be governed by differential equations like dy dt, find dx dy of yt dyt of by dt dxt of dt, so on and so forth. So and third is it consists of adders, multipliers and delay elements. These will be generally implemented in software or sometimes in hardware or both, whereas this will consist of resistors, capacitors and inductors, the analog filter. And the number 4 is filter coefficients are designed to satisfy the desired frequency response, whereas in case of analog filters, approximation problem is solved to satisfy the desired frequency response. And now coming to the advantages and disadvantages of the digital filter. Advantages and disadvantages. Advantages of digital filter. So let's come to the number one advantages. So basically what we are using here adders, multipliers and delays. We are not using resistors, capacitors and inductors, right? And the life of and the value of these components, it changes with time. So as we go on, as the components keep on aging, their values change and the analog systems will start to malfunction. Fine. So this is the first advantage is since digital filters have no electrical components, they will be having high thermal stability, right? With temperature and the second thing is digital filters are programmable, right? So filter coefficients can be changed at any time to implement adaptive features. So filter coefficients can be changed. So what does it mean? It means I can change filter coefficients. I can move from low pass to say high pass, low pass to say for example band pass, and so on and so forth. Right. And third one is a single filter can be used to process multiple signals. How? Because of multiplexing. Multiple signals. Why? Because of multiplexing. Fine. Okay, now coming to the disadvantages. These are the advantages. Now disadvantages or limitations. Number one will be bandwidth will be limited by sampling frequency. Limited by sampling frequency. It's basically half the sampling frequency, bandwidth of discrete signal. Half the sampling. Fs is equal to 2fm. Fine. So this is bandwidth of discrete signal. So it's limited by the sampling frequency, high sampling frequency. Second is performance depends upon hardware. How? It depends upon bit length of registers. It depends upon bit length of registers in hardware. Fine. So we'll stop here. This is end of the first basic lecture on the IIR filters. Okay, thank you.